We're now going to introduce the concept of the electric field. And the electric field is um, if you will, it originally was thought to be somewhat imaginary, like, it was just this ethereal substance that we invoked to explain things. It turns out that the electric field is a very real thing, as we will see once we get to light. But it was initially invoked to explain the behavior of how charges moved when they were near each other, how charged objects moved when they were near each other. And the way to initially think about the electric field is, suppose I have a large charged object with a large charge, capital Q. So when you see capital Q, you can think of something with a lot of charge on it, right? And what I'm going to do is I'm going to bring a small test charge, this Q sub 0. And the Q sub 0 is what we call a test charge. And a test charge is typically defined as a small amount of positive charge. A small particle that has a small amount of positive charge relative to the large object that we are trying to investigate the field of. Okay. And so the way to think about the electric field, or the way the electric field is originally defined, you can think of the reason that these charged objects, capital Q and Q naught, since they have the same sign, these are going to repel. And so you can think of the reason that these objects repel is due to the interaction of their electric fields. If all charged objects have electric fields, then it would potentially stand to reason that these fields are going to be what are responsible for why the charges feel forces in the first place. And so what we do is we define the electric field of our large object Q as the ratio of the force exerted on Q naught divided by the charge of Q naught. So basically what we do is, imagine we hold capital Q fixed. Imagine we, maybe glue this large sphere down and we smatter it with a lot of charge. And then I take a small amount of charge, put it on a small particle, and bring it into the vicinity of capital Q, of my large sphere, and then let it go and observe the force. See how the force acts on my test charge. Measure the force with, some instrument, a forceometer, if you will. And what I can do is take the ratio of that force that my instrument gives me, divide that by the charge on Q naught, and that would give me a measurement of the electric field that my large sphere was giving. Okay. So that is how the electric field is initially defined, right? If I take a test charge Q naught, bring it into the vicinity of a much larger, or an object with much more charge, I guess, if you will, and see how the force acts between the two objects, I can then get a representation of the electric field. Okay. Now, electric field lines, we define them to emanate from positive charges. So electric field lines will point away from positive charges. So if I look at my point P in the slide, point P, if I look at that point, the electric field is going to be pointing away from the positively charged sphere. Whereas if I look at point A, the electric field is going to be pointing toward the negatively charged sphere. So we define electric field lines to point away from positive charges, sources of positive charge, and we define it to point toward sources of negative charge. Another way of saying it would be that field lines originate or emanate from positive charges, and they terminate on negative charges. That would be another way of thinking about it. And so if I follow this to its logical conclusion, since we know that F equals, we know that F equals KQ over Q times Q over R squared, whatever my Q's are, right? But if we come back up here, we also see once again that E is equal to F over Q. And this F is the electrostatic force. So this F represents Coulomb's law. So if I solve this equation for F, I'm going to get F equals EQ naught. And so if I look at Coulomb's law in the lower left, I see that F equals KE Q naught over R squared. And so the electric field, if F equals Q naught times E, then I can take Q naught out of the Coulomb's law, and everything that I'm left with must be the electric field. So what this tells me is that the electric field of my source charge, what the capital Q in the previous slide is sometimes called the source charge, as opposed to the test charge. And so every charged object is going to have an electric field that is equivalent to Coulomb's constant times the amount of charge on my source charge divided by the distance squared between my source charge and test charge, okay? The square of that. So another way to define the electric field is to say if I have a charged object, the electric field is going to be proportional to the amount of charge and divided by the distance squared of the point where I'm trying to measure the field. And so again, because this is an inverse square law behavior, the closer I get to my source charge, the stronger the electric field is going to be, and the further out I move from my source charge, the less the field is going to be. Now, if I look at the two situations here, my plus Q with my test charge Q naught and my negative Q with my test charge Q naught, what I would do is I would actually measure the same field strength at point P, assuming that both Q's had the same amount of charge. Right, assuming that both sources, my positive and my negative sources, had the same amount of charge, and I go the same distance from them, I would still measure the same magnitude of the electric field at those points. It would just happen that the field in the positive case, the positive Q case, would be pointing away from the charge, away from Q, and in the negative case, it would be pointing toward Q. So this can beg a question: what happens if I have two positive charges along a straight line? And it does turn out that there is a position where the electric field is zero, and it must be. And if you think about it, this has to hold. For example, suppose right halfway between those two charges, I put a small test charge, Q naught. Which way would it be attracted to? Well, the charge on the left would push it to the right, and the charge on the right would push it to the left. But if the charges on both sides have the same magnitude, and the test charge is halfway in between them, so it's exactly equidistant, my R squareds in the Coulomb's law would be the exact same in both cases, then I'm going to have equal forces that are going to cancel out. So if I have equal forces on my test charge that cancel out, then at that particular point, vectorially, the fields cancel out, and there is a position where the field lines are in fact zero, or the field itself has zero magnitude. So working with electric forces and working with electric fields, here's a basic problem-solving strategy to help guide you through your problem-solving process. And I can't stress this enough. Number one, draw your field lines. Draw your field lines and draw your field lines. Draw a diagram of your situation. This will help you extremely immensely. Okay. Identify your charges. Convert all of your units to standard SI units, to coulombs, to newtons, and to meters. And then if you're working with forces, apply Coulomb's law. If you have to, work with your components. So break any forces that aren't directly along either of your axes into the x components and into their y components, and then use the Pythagorean theorem in trigonometry to actually then perform your calculations, get your resultants, and finish off the problem. Now, what do electric field lines, how do we actually visualize them? So for a set of point charges or point particles that are charged, the field lines, we envision them as being spherically symmetric around them. And again, the field lines are going to point away from a positive charge, and they're going to point toward a negative charge, right? And the number of arrows that I draw is supposed to be proportional to the field strength. So if I have a really large quantity of charge on an object, I would want to draw very dense lines. And if I have a very non-charged object, a very lightly charged object, then I'm only going to draw a few lines. Now, what happens if I bring these two types of charges near each other, right? And we'll start with the positive and negative case. And what you actually see is that we get this kind of butterfly effect, okay? So in between the two charges, the lines are going to connect and they're going to kind of bow outward. And then as you get to the opposite sides of each charge, they're going to kind of fan out a little bit. Now, technically, these lines are still going to connect, okay? Positive charges and negative charges, their field lines love to connect to each other, okay? And again, the number of lines in your diagram is going to be proportional to your charge. Now, one thing to note, your field lines cannot cross, okay? Your field lines cannot cross. They can connect, but they cannot cross. So we will not have any zigzagging patterns of our electric field lines. And that's important for the next case where I have two charges of the same sign, right? What do the field lines look like if I have two charges of the same sign? Well, in this case, the field lines are going to, the field lines that are in between the charges are going to try and move toward the other charge, but then they're going to bow outward, right? They're going to kind of repel each other. And it's this repulsion that we envision is actually the repulsive force, or the mechanism behind the repulsive force of like charges. Just as in the previous cases, in the previous case rather, the charges connected, the field lines connected, and that is the responsible mechanism for the charges attracting, right? So if I have two like charged objects, then in this case the field lines cannot cross in the center, they're going to bow outward, and what that means is you're left with zero field in the middle, and that is completely consistent with what we had earlier, our earlier statement. What happens if I have two charged objects that are opposite, but one is larger than the other one? Then I'm going to get to more exotic shapes, okay? Now, you don't have to read too much into this particular slide. We're not going to do too much with this one, but just know that the more different my charges are in magnitude, the more exotic the field line configuration can get. But again, the field lines cannot cross at all, and they can connect if you're going from a positive charge to a negative charge. But if you have two like charged objects, they must repel each other. Okay, they will not crisscross. So to finish out this video, let's think about this. If I want to look at this particular picture and rank the magnitude of the electric fields at points A, B, and C in the figure below, I want to rank them from largest first down to the smallest. Well, remember the field lines go as the inverse of the square of the distance. So what that means is the closer to a charge I am, the stronger the field. So that would imply that A is going to be the strongest point. Now, with that being said, B seems to be further from my second charge than C is to either charge. But remember what we said before. In between two positively charged particles or negatively charged particles, two like charged particles, the field is going to be zero at some point. And in this particular case, it certainly looks like the field is zero at that point. Whereas at point B, the field is non-zero, but B is further from its charge than A is to its charge. So ranking these in order, we would say that the order is A, B, C. Okay? So I hope that makes sense, and we will see you in the next video.